Have you ever wondered what makes it possible to support life on Earth? Have you ever wondered why the temperature on Earth is changing? Have you ever wondered why the sun is as hot as it is? There are many things that people wonder that are left unanswered. Today, all of your questions about Earth's energy will be answered. Welcome to Beyond the Horizon, the range of climate change. Hi, my name is Jaden.
Hi, my name is Zoe.
Hi, my name is Shira.
Hi, my name is Ronnie.
Hi, my name is Nola.
I'm an expert on how the temperature of the Earth system varies over time and the causes of these variations.
I'm an expert on the structures of the Earth system, atmospheric and terrestrial.
I'm an expert on the main causes of climate change.
I'm an expert on the difference between weather and climate and extreme weather events.
I'm an expert on how energy flows into, out of, and within the Earth system. I will also discuss the three main energy transport mechanisms: conduction, convection, and radiation.
The temperature of the Earth system is greatly affected by things like elevation and ocean currents. For example, the El Niño Southern Oscillation is a cycle of changing wind and ocean patterns and currents. And an El Niño phase can warm the water in the Pacific Ocean. Elevation can also affect the temperature by decreasing it with every 100-meter increase in elevation. There are several methods that can be used to determine temperature, like weather stations, weather balloons, and thermometers. The angle of solar radiation affects the temperature of a location at different latitudes because the angle of radiation depends on the latitude. To study past temperatures, a paleoclimatologist can uncover clues about our current and future climate using many sources.
Have you ever wondered what the layers of the atmosphere are called? The lowest layer of the atmosphere is known as the troposphere. This layer makes up 75% of the Earth's atmosphere and also contains 90% of the Earth's water. Almost all of the weather happens in the troposphere. Air temperatures in the troposphere typically decreases as altitude increases, as a result of three mechanisms of heat transfer. Solar radiation passes through Earth's atmosphere and heats up the planet's surface. The oceans and land absorb approximately half of this incoming solar radiation, while a small fraction is emitted back into the atmosphere as infrared radiation. The next layer is called the stratosphere. It extends upwards approximately 50 kilometers from the troposphere. Ozone, a form of oxygen with 3 atoms per molecule, is concentrated in the stratosphere. Ozone absorbs most of the ultraviolet radiation coming from the sun, preventing this radiation from reaching Earth's surface. Ozone is harmful to living things because it damages and destroys cells. Above the stratosphere lies the mesosphere. This layer stretches to approximately 90 kilometers above the surface of the Earth. In this layer, the temperature goes down again. Weather and climate are always changing. While I was researching, I found extreme weather conditions all over the world. These are just a few of the things that happened in 2014. First of all, in Argentina, they had major heat waves. It was the second warmest year, behind 2012, since national records started in 1961. In Australia, there were also heat waves. It was the third warmest year, warmest spring on record, and the third warmest autumn. These are just a few things that happened in 2012. Weather and climate always move and change. One minute it could be the coldest it's ever been, and next it could be the hottest. Thanks for listening to my segment on weather and climate change.
There are many natural causes that influence global climate changes in different ways. Radiative forcings are any factors that cause these changes to the energy balance on Earth. These are either natural or human-caused forcings. The Milankovitch cycles are 3 cyclical changes in the way Earth orbits and tilts. These changes in Earth's tilt cause more snowfall in the northern latitudes by creating water vapor in the air. Volcanic eruptions spread dust and bacteria into the air, which leads to global cooling. Global wind patterns are created by uneven heating on Earth's surface, drive ocean surface currents, and the many types of global wind patterns have different outcomes. Trade winds travel back to the equator warm and steady. Polar easterlies are cold air approaching the north and south poles. Additionally, solar radiation leads to warm water flows. Sunspots are darker areas on the sun's surface from the weakening of gases that transport heat energy from the sun's interior. This is caused by an intense magnetic field. When there are more sunspots, this causes the climate to be warmer. El Niño's southern oscillation is oscillation of ocean and atmospheric systems in the tropical area of the Pacific Ocean, which affects global weather. Southeast trade winds blow across the tropical Pacific Ocean towards the west, but these winds weaken, causing warm water to flow towards South America. El Niño is the warmest water phase, and it leads to benefits such as less hurricanes.
Quiet on set, go.
Next, there are many types of greenhouse gases that cause consequences to the Earth, such as the decrease in pH in the ocean and the production of fossil fuels in Celsius. This alters the balance between incoming and outgoing radiation, which determines the Earth's climate. Humans are also contributing to this issue by producing cement, burning fossil fuels, and starting forest fires, which all lead to the production of carbon dioxide. Carbon dioxide is harmful because it leads to the ocean pH being decreased, which lowers availability of carbonate ions needed by organisms that build shells. When rainwater dissolves, carbonic acid is also formed. Methane can be formed throughout different types of farming, which humans also cause.
Action.
There is still hope to get rid of carbon dioxide through photosynthesis, deposits in sediments on land or in the ocean, and dissolving it in water. Photosynthesis is when plants use sunlight and carbon dioxide to create energy and oxygen in the earth. There is a general trend to this, and it slightly matches the observed model. After playing with these forces, I discovered that El Niño is the forcing that contributes the most to variability in temperature, and solar contributes the least. Next, when I was studying energy on climate, I learned that there is an equal balance between radiation on both Earth's surface and atmosphere. The energy gained on Earth's surface, which is made up of absorption of solar radiation and absorption of infrared radiation from the atmosphere, and the energy lost on Earth's surface, which consists of heat loss by evaporation, heat loss by conduction and convection, infrared radiation emitted to space, and infrared radiation absorbed by clouds and greenhouse gases, both added up to 147 units. For the radiation balance on Earth's atmosphere, the energy gain was from absorption of solar radiation from the atmosphere, absorption of infrared radiation from the atmosphere, latent heat released by condensation of water vapor, and sensible heat released by convection and conduction. This added up to a total of 160 units, which is equal to the energy loss that was from infrared radiation emitted to Earth and emitted to space. This proves the equal radiation balance between Earth's surface and atmosphere.
Many people may think that climate and weather are the same thing when actually they are very different. They vary in their definitions themselves and the ways in which they are forecasted. Weather is defined as the state of the atmosphere at some place in time. It is usually expressed in terms of temperature, air pressure, humidity, wind speed and direction, precipitation, and cloudiness. Climate, on the other hand, is defined in the terms of the average of weather elements, an example being temperature or precipitation over a specified period of time. The Köppen system divided climate into 5 main types. These types are tropical, dry, moderate, continental, and polar. Now to talk about the different methods of forecasting. In order to forecast weather, meteorologists focus primarily on real-time data to predict local or regional atmospheric conditions for the hours, days, or weeks ahead. Thus, weather prediction tends to be more local and relates to conditions in the immediate future from days to weeks. In comparison, in order to forecast climate scientists look at atmospheric conditions in terms of averages and trends that have occurred over many decades, centuries, and millennia. Although weather is variable, it can be averaged over time to indicate climate trends. Therefore, climate scientists can use weather data to help them identify previous trends and improve their predictions of future trends. Climate scientists also use increasingly higher resolution computer models, known as global climate models, to simulate the physical process of the atmosphere and oceans to make predictions about future climate scenarios. Scientists also use something called proxy data. Proxy data includes biological, cryological, which refers to frozen water, geological, and historical records that scientists use to work out Earth's atmospheric conditions in the distant past. Now moving on to the significance of extreme weather events.
The big question that I normally get asked is, how does the sun get its energy? The answer to that is, the sun gets its energy from a process called nuclear fusion. Nuclear fusion is the fusion between hydrogen and nuclei. 4 hydrogen nuclei are fused, forming a helium nucleus. Energy gets released because the helium nucleus has a slightly lower mass than the 4 original hydrogen nuclei. That's where the formula E equals mc squared comes from. E stands for energy, M stands for mass, and the C stands for the speed of light. The sun also gets its energy from electromagnetic radiation. The energy makes its way to the outer regions, and the sun is radiated or emitted away in the form of energy. That's also why the sun is so hot. Electromagnetic radiation is made up of electromagnetic waves. Electromagnetic waves are waves that cause charged particles, for example, electrons that move up and down. These electrons have electrical and magnetic properties that can travel through gases, solids, and space, and travels 300,000 kilometers per second, which is the speed of light. Electromagnetic waves are characterized by wavelength and frequency. Because I'm talking about electromagnetic waves, let's take a look at the electromagnetic spectrum. The electromagnetic spectrum represents the complete range of electromagnetic radiation. The region of the spectrum with a shorter wavelength than the color violet is referred to as ultraviolet radiation, and the region of the spectrum with a longer wavelength, that is the color red, is referred to infrared radiation. There's also something called solar radiation. This type of radiation is a type of radiation that reaches the Earth. The sun emits radiation at all wavelengths. Approximately 44% falls within visible light wavelengths. In conclusion, the sun derives its energy from nuclear fusion, specifically the fusion of hydrogen nuclei to form its helium nuclei, releasing energy due to all the mass difference as described by E equals mc squared. This energy in the form of electromagnetic radiation including visible light, travels through a space as electromagnetic waves. These waves, characterized by their wavelengths and frequencies from the electromagnetic spectrum, with ultraviolet radiation having shorter wavelengths than violet light, and infrared radiation having longer wavelengths than red light. Solar radiation emitted across all wavelengths, including visible light, accounts for about 44% of the energy reaching Earth, with the sun behaving like a black body, absorbing and emitting radiation efficiently. Temperature and radiation is very important as well. When an object is hot enough, you can see the radiation it emits as visible light. The Stefan-Boltzmann law is a fundamental law that explains the relationship between an object's temperature and the amount of radiation it emits. This law states that all objects with the same temperatures above absolute zero emit radiation at a rate proportional to the 4th power of their absolute temperature. Another important law is Wien's law. The higher the object's temperature, the faster the molecules will vibrate and the shorter the wavelength will be. The hot sun emits radiation at a relatively shorter wavelengths, with the maximum emission in the visible light region of the spectrum, whereas the relatively cool Earth emits almost all of its energy at longer wavelengths in the infrared region of the spectrum. For this reason, solar radiation is often referred to as short-wave radiation and terrestrial radiation as long-wave radiation. Lastly, to sum everything up, the Stefan-Boltzmann law, represented by E equals QT with the to the power 4, explains how the radiation emitted by objects is directly related. Lastly, to sum everything up, the Stefan-Boltzmann law, represented by E equals QT to the power 4, explains how the radiation emitted by objects is directly related to their absolute temperature. Wien's law, wavelengths times max equals constant divided by time, demonstrates that higher temperatures lead to shorter wavelengths of radiation. The sun emits short-wave radiation due to its high temperature, while the Earth emits long-wave radiation because it's cooler. Heat transfer involves conduction, where heat moves directly between substances, and latent heat, which is absorbed or released during phase changes such as evaporation and condensation.
I focused on how the concentration of atmospheric carbon dioxide has changed over the past 800,000 years and since the Industrial Revolution. While experimenting, I saw that the change of CO2 concentration varies between the years, and the pattern that is shown in the graph goes up and down. The CO2 changes by increasing throughout the past hundreds of years. In the video, you can see an extreme spike in atmospheric CO2. The atmospheric CO2 varies over a year because during high growth periods, or summer, the more CO2 is absorbed, but then during winter, less CO2 is absorbed. Another example is the northern and southern hemisphere. They're similar to summer and winter because the northern hemisphere is warmer, just like summer, and will absorb more CO2. In the second graph, the northern hemisphere shows more variation in the change over time and between summer and winter months. For example, in the time period of 1979 to 2012, the difference in CO2 concentration increases by 27 ppm or parts per million. And in 1750 to 1850, the difference in CO2 increased by only 6 ppm.
Okay, it's done.
Over the past 8,000 years, the CO2 has increased and decreased every few hundred years. In my investigation, I had to calculate the estimated rate of change for 3 sequential periods of extreme low to high concentrations of CO2. When I calculated it, it showed the average rate of change in the past 200,000 years is around 0.8 per 100 years, and with an increase of 0.1 per 100 years in the past 100,000 years. The CO2 and temperature pattern basically overlaps each other, which shows that they have a big correlation to each other. To sum it all up, basically when temperature increases, CO2 increases.
I explored the temperature changes caused by different types of forcings. I focused on El Niño forcings, volcanic activity, solar forcings, and anthropogenic forcings. The temperature had the biggest change when the El Niño forces were active, specifically during the years of 1984 and 1998. This partly followed the observed model predictions. The temperature does not increase when the volcanic eruptions, but there is a decrease during 1983 and 1992. This pattern only matches the TA observed model during these times when there is a lot of volcanic activity. The solar pattern has very gradual increases and decreases, and it does not match the TA observed model. Lastly, the anthropogenic force is only increasing and is continuing to increase from 1980 to 2015.
In my investigation, I explored the topic of extreme weather events, specifically heat waves. Many places around the world experience heat waves, mostly during the warmer seasons. And unfortunately, sometimes these heat waves result in people's deaths from heat-related causes. Now to define a heat wave. The common definition of a heat wave is that a heat wave is generally a period of several days to weeks of abnormally hot weather that may or may not be accompanied by high humidity. The World Meteorological Organization defines a heat wave as 5 or more consecutive days of temperatures 5 degrees Celsius or 9 degrees Fahrenheit above the average maximum temperature. Because the average maximum temperature varies from one location to another, what is considered a heat wave in one location may not be considered a heat wave in another. In order to collect data, I had to research the daily temperatures for all of June, July, and August in Washington, D.C. I then turned my data into a graph which is shown here. While recording my data, I discovered these few things. That in these last 3 months, the highest that the temperature ever got to was 102 degrees Fahrenheit, and that throughout those 3 months, Washington, D.C. experienced 3 heat waves. I observed certain trends in the data that I collected, some being that the temperature varied day to day and that the temperature stayed mainly between 70 to 90 degrees Fahrenheit. In my investigation, I was asked the question, why do you think that heat-related mortality can be greater in cities at higher latitudes than in more tropical cities? Here's what I came up with. I think that it's because 1, these particular cities may not be used to the hot and humid weather unlike some tropical cities. 2, they are so very not used to this kind of weather that almost nobody invested in an air conditioner, leaving many people lacking the technology to stay cooler during the hotter seasons. And 3, I found out that many people of these cities suffering from these heat waves and heat-related mortality have a much older population, making these people more vulnerable to these hot and humid temperatures. I researched that in the last few years, the amount of people who have died from heat-related reasons changed a lot. In 2018, 1,008 Americans died as the direct result of heat exposure. And in 2021, heat-related deaths increased to 1,600, a 59% increase. It turned off. I had like 10 words left.
Then just say those 10 words.
Okay, just
go from where you... Nola will cut that part out. Just go from where you left.
Just the last sentence. I'll start from like the last sentence. Okay, is it?
Yeah, it's still going.
Oh, it's still going? In 2018, 1,008 Americans died as a direct result of heat exposure. But in 2021, heat-related deaths increased to 1,600, a 59% increase from only 4 years earlier, and a 439% increase from 2004.
The mesosphere's lower temperature results in part from the low concentration of ozone, so little solar radiation is absorbed in this layer. Humans cannot survive in this layer because of how little air pressure is in this layer. The thermosphere lies above the mesosphere and extends approximately 600 kilometers beyond Earth's surface. The International Space Station circle our planet in the thermosphere. The temperatures increase again in this layer. For most of Earth's history, life on Earth was made up of simple marine animals. Earth has a relatively thin atmosphere and is made up of 78% nitrogen, 21% oxygen, and 1% several inactive gases. Examples: argon, neon, helium, hydrogen, and xenon, and several other gases that vary in concentration: water vapor, carbon dioxide, methane, nitrous oxide, ozone, and chlorofluorocarbons. Water vapor and carbon dioxide make up a very small amount of Earth's atmosphere, but they are very important because of how good they are at absorbing heat.
What is the first law of thermodynamics?
Well, according to my calculations, energy coming in and energy coming out is a huge part of it. Solar energy gained from the Earth and its atmosphere is equal to the infrared radiation emitted from Earth and its atmosphere to space. This is also called the law of conservation of energy. A lot of people ask me what range of wavelengths is outgoing terrestrial radiation. Well, shorter wavelengths, because the 51 units consist of shorter wavelengths because it's the energy that contains the most heat. I also know because longer wavelengths are way cooler and shorter wavelengths are hotter. And the Earth emits long wavelengths and the Earth absorbs short ones. The Earth's atmosphere has the ability to absorb heat. The Earth will absorb more energy than it emits, because if there will be more greenhouse gases which are able to absorb heat, Earth will absorb more energy than it emits.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.